Так, давайте поймем, здесь есть кто-нибудь англоговорящий вообще?
А по-русски рассказывайте.
Ну, не знаю. Не
Вы
знаю.
хотите... Один человек.
Один человек, да?
По крайней мере, один.
Угу.
Ну, вы решайте, как бы... Это...
Ну, давайте начнем по-английски, а там, если плохо пойдет, то перейдем на русский.
Окей. Женя, давай, включай. Okay, we are starting our last talk this evening, and we are very delighted to have here one of the leading scientists in machine learning in Russia, Konstantin Vorontsov, who is professor of High School of Economics, Department of Computer Science, and also professor of
of Moscow Institute of Physics of Technology at first.
Yes. And Yandex
School of Data Analysis.
School
Yes.
Of Data Analysis. Okay.
Thank you very much. My talk will about probabilistic topic modeling and about my thoughts about how to use this technique for question answering task. The last part of my talk will be from my PhD student Anna Potapenko. She will talk about links between topic models and other word embedding techniques. And my talk will about topic modeling. Some interesting, maybe a little demotivation words about this contest. I think that this problem, the challenge, is not very interesting because of three demotivators. First is that this data set is not true test for general human knowledge because this test ignores important aspects of human intelligence. Maybe for some informal discussion, I will use Russian. Когда я записался на курсы вождения, то инструктор по вождению сразу спросил меня: вы для чего к нам пришли? Для того, чтобы сдавать экзамен или для того, чтобы учиться водить по городу в Москве? Ну, я, как всякий здравомыслящий человек, тут же сказал: ну, конечно, для того и другого. А он мне говорит: нет, так нельзя. Это невозможно, это по-разному надо учить. Точно так же с тестами ОГЭ, ЕГЭ, когда школьники должны отвечать на 4 вопроса, то есть на вопросы и выбирать из 4 ответов. Вопрос: это инструмент измерения, как он позиционируется, или это цель обучения? Так вот, очень легко скатывается ситуация к тому, что это становится целью обучения. И как и в автовождении тоже. Вот. Я не хочу обсуждать, на самом деле, этот вопрос. Это мое личное отношение к таким тестам. Я считаю, что они губят идею обучения на корню, и мы перестаем иметь мыслящего человека. Создается психоз, в который вовлечены все стороны, учителя, школьники, их родители, и целью обучения становится сдача этих тестов. Вот. Поэтому я считаю, что тренироваться на таких тестах – это антигуманно. The second demotivator is that here very simple methods will work. This is not a true artificial intelligence technique because big data computation and simple heuristics from information retrieval will work. And one of the goals of my talk is to show that this is really the case, and this sample statistical methods will work. And the third thought is that your implementation that you will do during this hackathon will not a true question answering system. Because real-life query answering systems retrieve information from the web, and they solve an order of magnitude more complicated task. How to rank 1,000 potential answers, but not 4 answers. This slide is about a basic statistical approach that I should use myself if I should participate in this challenge. First step that all of you understand very well, much better than me, that you must download external collections such wiki, such textbooks, etc. Then there are many sources of information. And this is the main text collection, not the collection of questions and answers. The main data set is external collection. It's more important. This collection contains all information you need. Second step is pre-processing these texts and vocabulary generation. There are some non-trivial things about what must be the entries of this vocabulary, and I will discuss these issues later. Third step is splitting each text into appropriate segments. What is appropriately offered the segment of appropriate proper length? What is the optimal length of segments? I think that each segment that you find in a wiki or textbook, etc., it must know not so short and not so long. It suggested to contain a question and an answer. So the segments must be as short as possible for contain simultaneously question and answer. This is the idea how to determine what is the document in this external collection. Overall textbook is not a document, and overall paper from document from Wikipedia is also not a document in our sense. Fourth step is optional. We must expand query or question in our case by synonyms, by coherent words, or something else that will help us to find a segment relevant to the question, even in this segment the question is reformulated, restated. Fifth step and sixth step is how to define the relevance of a question to a segment and of answer to a segment. This may be a probabilistic measure of relevance or just a heuristic similarity measure that compares two text strings. After this, you define the relevance of answer to a question. And the structure of this formula shows that you must first find your question in segments overall external collection. and multiply the relevance of question to the segment for answer to the segment. And after summarization, we will have aggregated measure of relevance of the answer to a question. You are free to invent your own functions here. This is a heuristical approach. What is important? Non-linearity, but monotonicity, of course. And what is the main sense of this formula? We have to augment the accuracy by the fact that we have big data, and so we may have many places, many segments that contain answer of each question. Therefore, we must aggregate these answers. And all these steps are purely statistical and heuristical. And therefore, you may invent many measures of relevance, dozens of thousands of such measures. And after this, I propose to solve a machine learning task, supervised machine learning, because you have a set of true and false answers to each question, and you can use this data as a training set and to learn some classifier which will classify your test pairs of questions and answers. This is the idea, this is the common scheme how to you may solve this challenge. But there are steps in what each of perform by some unique way. And these variants and options I want to discuss. Step 2, preprocess text and generate a vocabulary. There are many little things that you may do at that moment. Of course, you will use stemming for English text. You may use stop word lists. You may use TF-IDF for words filtration. You may use some tools for named entity recognition, for term extraction, etc. But I think that from this list, the first and the last are most important. You must use stemming, of course, and you must use n-grams extracted from questions, not from overall external collection, because too many b-grams and 3 grams will be extracted, and the vocabulary will be enormous in such case. And here we may use the fact that we have a little set of relatively short questions, and the vocabulary of b-grams and 3 grams from these questions will not be so large. The next step, split each text into segments. There are some ideas. The first one is to choose each segment of 1 or more paragraphs, which restricted length. Another idea is to choose sequences of sentences with some another restrictions, because sentences are shorter than paragraphs. And a good idea to use half overlapping segments. Bricks-like. Because you may have here a question and find here an answer. if you use these bricks, you don't understand that they are in the same segment. The next. How we can expand the question? There are a big thing in search engines about how to expand queries, and all these well-elaborated techniques may be used here. The first is to use synonyms from well-known linguistic resources. The second one is to use coherent words, the words which are frequently frequently occur near to each other in external text collection. And the third is to use techniques of word embeddings, for example, topic model, word2vec on other global vectors, etc., to extend questions and to solve the problem of synonymy, because the formulation of question in question data set and the formulation of question in external text may be not coincident by words, but they may be very similar if we use synonyms, coherent words, etc. And what is synonyms is not clear, and external linguistic resources are sufficiently complete is not clear. Therefore, we hope that the word embedding techniques will help us to construct better similarity measures between short texts. The next step is to define relevance measures of similarity measures between two short texts. Here, the second argument is always a text segment, and the first argument X is our question or our answer from the challenge data set. We always believe that the length of X is shorter than the length of S, of segment S. How we can compare this to text? First first idea is to compare them as bag of words. This is the most simple approach. The second is to compare them as distributions of vocabulary. And here you can take into account the frequencies of each word in overall collection. And third way is to... third way is to compare this text as the vector representations. And topic models and other word embedding techniques are useful to question expansion and to define relevance measures. Some examples of... Yes? Нет, ну как он может зависнуть, если я его листаю? Let us continue. Here you can see examples of some relevance or similarity measures to compare text X and segment S. Of course, another variants are also possible. The first is Jacquard similarity that compares two texts as a bag of words. Second and third divergence similarities are used to compare them as probability distributions. First is not symmetric measure, and second is symmetric measure. And both are based on Kullback-Leibler divergence, and exponent makes similarity from the distance. And also cosine similarity, which is very frequently used in information retrieval works. How we can use relevance measures to build machine learning application for query for question answering. There are many variants to define combinations of preprocessing options, of document splitting, of question expansion and similarity measure. And if we multiply the number of variants, we obtain more than 3,000 of features. This is a good feature space, sufficiently long, maybe too long, and we may use many techniques from machine learning. We may use feature selection, SVM, gradient boosting, neural networks, etc. The next part of my talk is about topic modeling. So we have two reasons to use word embedding techniques, and topic modeling as particular case, to query expansion first, and to define similarity measure at second. What is topic for topic modeling? Intuitively, it is a specific terminology of a particular domain area or a set of coherent terms that often occur in documents. More formally, a topic model uncovers latent semantic structure of the text collection. And for our task, this is, of course, external collection of big texts, like Wikipedia, textbooks, etc. But also questions can be considered as documents and may be or may not to be. There are variants how to consider questions in this application in question answering. So the main motivation to use probabilistic topic modeling is to define the adequate semantic similarity, which maybe is more powerful than the lexical similarity. And topic model defining this latent semantic structure defines each topic as a probability distribution over terms, and each document is a probability distribution over topics. This means that the collection is generated by the two-step probabilistic generative process. First step generates a topic for each position of each word, in documents. And the second step, knowing when we know this topic, you may choose a word from distribution of words or terms of this topic. And thus, word by word, you generate the text. Of course, this is a model of bag of word generation, not the text which will be interpretable, understandable by human. In such a process, you can only generate a text up to arbitrary permutation of terms in this text. But our task is the inverse problem. We have text document collections over a vocabulary of terms. We know how many times each term appears in each document, and our task is to find probability distribution of words in each topic and of topics in each document. And this problem is obviously mathematically a problem of matrix factorization, non-negative matrix factorization, where the columns, vector columns of two matrices, phi and theta, are probabilistic, discrete probability distribution. But the problem of matrix factorization is posed. You haven't a unique solution. You may use a matrix S and inverse S and obtain two another matrices phi prime and theta prime that multiply the multiplication of these two matrices are equal. This is a fundamental issue for topic modeling and other matrix factorization technique, because you may because the method, numerical methods that give you matrices phi and theta from initial text collection may give you an arbitrary solution. And you must control this process, but in standard methods you haven't instruments to control what a solution will be found by the numerical method. Historically, probabilistic latent semantic analysis was the first method to solve this problem. It is based on optimization task, constraint maximization of log likelihood, and the solution from Karush-Kontaker conditions is a system of equations. This is a system of equations with auxiliary variable p TdV. This is auxiliary variable that have a very nice probabilistic interpretation. This is the probability distribution of topics for each term in each document. So this is a strictly latent variable representation of text collection, because we have terms in documents. They are observable variables, but a topic for each term in each document is hidden. And here, this formula says that you attempt to discover what was the topic, hidden topic of each term in each document. Another equations in this system are strictly the frequency estimates of conditional probabilities, because here you have a conditional probability of a topic for each term in each document. If we multiply this conditional probability to a number of occurrences of term in document, and then if we sum these over all documents, we obtain how many times overall collection the term W was from the topic T. And normalization gives us a conditional probability. And by analogy, we can interpret this formula for theta matrix as conditional probabilities, as estimates, empirical estimates of conditional probabilities of terms in each document. So the system of equation is very simple interpreted, because the first formula is no more than bias rule for this conditional probability, and the formula of M step are frequency estimates of conditional probabilities. This is important to understand how PLSA works. So this is iteration process which estimates conditional probabilities of topics for each term in each document from phi and theta matrices, which are parameters of the model, and then recalculates these parameters from auxiliary variable p. This is iteration process also called the EM algorithm, and the view of this process not from the probability theory but from the optimization problem gives us a possibility to and well understanding how to make the solution unique and stable. So we must use some regularization to add in initial optimization problem. The first attempt was LDA model. This is the most well-known model in topic modeling and most citable paper of David Blay, Andrew Ng, and Michael Jordan. The idea is to use the Dirichlet prior distribution and to say that vector columns in our matrices phi and theta are generated from the Dirichlet distributions. If you use maximum a posteriori probability to estimate the model parameters phi and theta, then we obtain the same very similar system of equations, which differ from the previous one only in additional constants in formula of M step. This means that we use Bayesian smoothing for frequency estimates of conditional probability. So the interpretation is very natural and very simple. But you can generalize this approach. We can use any regularization criteria, additional criteria, and if we repeat all steps that leads to this system of equation, we obtain the formula of m step, very general and very simple. You must only partially differentiate your regularizer by parameters of your model. So there are many topic models that are first introduced in Bayesian approach that can be very easy restated and reinterpreted in terms of non-probabilistic regularization. So here you must not use regularizers that have any probability interpretation. For example, what natural requirements to matrices phi and theta we can use and formalize to give better topic models? The first requirement is that that we believe that there are topics interesting to us, and there are background topics that are not interesting. They contain common lexis words, and therefore, in each document, we want to see a little number of specific topics. Many words in each document are interpreted as background, as common words, and they are not interesting for us. And also we want to use sparse and decorrelated topics in the specific topics parts of both matrices. So these topics are specific, and specific topics each document usually contain a little number of such specific topics. How we can express our requirements for sparsity and decorrelation in our regularized problem? The first, we want to express our requirement to have smoothed background topics. We formalize this requirement by a very simple way. We say that the vector columns that correspond to background topics must be near to a given distributions. And interesting that if we express this requirement via Kullback-Leibler divergence, we obtain the equations for m step strictly the same as in LDA, latent Dirichlet allocation model. But another strategy to obtain sparse column vectors gives us a regularizer that don't have any probabilistic interpretation. If we compare the previous case of smoothing and the next case of sparsing, you will see that the only difference is that here you have a minus. This minus leads to sparsing, and many values in phi and theta matrices will be zero because of this negative term. But no probabilistic prior have such properties in Dirichlet allocation. In Dirichlet prior in Dirichlet prior distribution, only positive values of parameters alpha and beta are possible. Negative are not possible and don't correspond to any known probabilistic prior. The next good idea is to make domain-specific topics as distant as possible. This can be done by maximizing covariances between column vectors phi and leads to a formula of m-step, very simple and very interpretable, that says if we have in a row of the phi matrix maximum value, then this maximum value in a row will be greater, and other values in this row will be smaller and smaller during iteration of EM process. That is the decorrelation happens due to this regularization criteria. This is also a very interesting regularizer that can solve a problem of number of topics determiner. This is a very important problem in topic models. The question how many topics there are in this collection. So this idea is to set initially the excessive number of topics, and then to use the regularizer, which will sparse the distribution P over topics. And this distribution depends on theta matrix. And the m-step says us that small topics during iterations of EM algorithm will vanish as rows of the theta matrix. Now, this strategy of topic selection is much easier to understand and to realize and to implement that hierarchical Dirichlet process that is a state-of-the-art approach to determine the number of topics in topic modeling. So the next interesting thing is that we can combine topic models due to the property of additivity of regularizers, and formula are not so difficult to understand and implement, and this is very very important to us to have a possibility to combine several models as regularizers in one generalized model. The next generalization of this approach is to use not only words or terms in our document, but to treat documents as universal containers that may contain not only terms but also metadata about documents such as authors, timestamps, sources, etc. Objects on images, links between documents, advertising banners if we say about topic model of web, users of documents who read, likes, download documents, etc. Can be also treated as elements of a finite set, of a finite vocabulary, and treated as a special type of words, of terms in documents. And all these modalities can be used to construct a single general topic model. This generalization is also not so difficult. We again use the property of the additive property of log likelihood, and we sum several likelihoods, each for each modality, and we take a system of equation very similar to that we have previously. So this approach is very general, is much easier to understand and to make the inference of the algorithm. In Bayesian approach, the inference is usually very complicated, but in our approach, you must only have a regularizer and differentiate it by parameters on the model. That's all. And you can reinterpret and re-implement many topic models and also their combinations that are known in the literature on topic models. This approach is very flexible from mathematics, but it can also be implemented in parallel and online implementation. And we did this in our project that we call Big IRTM, Big Additively Regularized Topic Models. It is open source. You can start to use this problem from the documentation, and we have very permissive license to use it both in scientific and commercial projects. I think that I don't know, I don't have a time to speak about the online EM algorithm implementation in this system. But the summary is that our approaches reduces barriers to entry into probabilistic topic modeling for practitioners because they may concentrate on the task, on the formalization of criteria and requirements for the topic model, rather than mathematical inferences and integrating out some variables. Technologically, this approach is good because it may be implemented in online parallel algorithm with linear time complexity. Linear by the length of collection and by a number of topics, and by number of iterations over all collection, that for big data may be only one iteration, for very large collections is usually sufficient to construct the topic model. Some experiments that show that our big RTM project works faster than concurrent, very well known projects from GenSim and Wopel-Wabbit. Another experiment is about the possibility to build a regularized model that has the same likelihood as not a regularized model, but from other criteria, for example, from sparsity, the regularized model will be much better. So unregularized PLSA model gives us a sparsity about 10% of zeros. In relation, we built a model which have more than 80% of zeros inside thematics, but their perplexities or log likelihoods are almost equal. One more experiment is about n-gram models. If you use b-grams as vocabulary entries, you can you can give much better topics from the point of view of the interpretability. This topic model was built on collection of scientific papers for our conference. I am a program committee member of these conferences, so I very well know this collection. And I know what topics are inside this collection. And when I see the topic in terms of unigram, I don't understand what is the scientific direction of scientific school or authors of this topic. But if I see b-grams, I know authors of these papers without looking inside these papers. And this is two topic examples, but this picture is general for the topic model. Topic models on b-grams are much better than topic models over unigrams, and this is the reason why in question answering you is preferable to use b-grams as elements of the vocabulary. So let us return to question answering. What may be ideas of using topic models and what ideas of regularization? First, this is the idea to use b-grams and 3-grams, but you can use them as additional modality. So each text can be represented both in unigrams and in b-grams and 3-grams. This is 3 different representations of the same text. So you can use 3 modalities and use multimodal regularized topic model to obtain well-interpretable topics. Second is using background topics to separate specific terms that frequently occur in questions, and common lexes that is not in for your task. And to make the model more interpretable, it is possible to use a combination of regularization criteria that are known to augment the interpretability of topics. My recommendation is to use decorrelation and smoothing of background topics. Decorrelation makes topic different, and secondly, the effect of decorrelation is that common words are extracted from specific topics and transferred to background topics. Also, topic model can be used to define the similarity measure, and the recommendation from this paper is to use an averaged Jensen-Shannon divergence to define the similarity between topics. So this idea, the idea is to the idea is to use a matrix phi for if you use a column vector corresponding to the topic T, and you can compare two vectors, two texts. The vocabulary corresponds to the rows of this matrix, and your text X is a subset of words, and another text is also a subset of words. And you must compare this, let us make it overlapping. You must compare this to this two set of words. So the idea is to make a projection of the overall distribution over terms of vocabulary on first subset of words and second subset of words, and then to compare this projected discrete distribution by Jensen-Shannon divergence. And the second idea is to use, again, Jensen-Shannon divergence, but to compare similarities between columns of the second parameter matrix theta. Two columns corresponds to documents EX and S, and you can compare them as probability distributions by Jensen-Shannon divergence. And the third idea is to aggregate these two similarities Y multiplication. This is a question to the authors of this paper. And alternative idea of using topic model for question answering system is to use one-to-one correspondence between questions and topics. So each topic becomes a separate question, and we can use a smoothing regularizer to say that this word distribution in this topic must be similar to the bag of words of our question, and there are one-to-one correspondence between questions and topics. And this is good idea because we have a predefined interpretation of each topic, and we can manually verify if our topic model really performs the question expansion. So we see the question, we see the most probable terms in this topic, compare them, and verify, is it possible to interpret this topic as question expansion? Are the words synonyms or coherent words to the words of question? Here are the references, and I invite Anna for the last third of the talk. I think that questions will be common to us, and we will answer your questions after Anna talks. Thank you. Да, подивись.
А есть указка?
Компьютер.
Сильно. Тогда все-таки вопросы, видимо.
Может, пока на вопросы ответить?
А где все слышно?
А то компьютер повесит.
А когда вопросы не запишешь, это самое главное. Нет, вопросы пишем.
Работаем на камеру.
А трансляции продолжаются. Мы сейчас просто спускаем.
Может, действительно вопрос получить?
Да, да.
Скажите, отвечайте.
Ну, тогда мне нужен микрофон.
Логично.
Нужен микрофон или можно и так?
Лучше, конечно. Лучше обоим зададим вопрос.
Ну, если образовался технический перерыв, то давайте я пока поотвечаю на вопрос.
Models are useful tool to describe big document, discrete probability distribution or topics. But what about a very short document, just a few words? Maybe we can use RTM or but maybe it's not so good way.
My opinion is that we have problems not with short documents, but with long documents. Because in long document maybe неоднородный. Not uniform. No. Yes, in homogeneous, and if you divide a long document on segments that are homogeneous, this will the beta solution. And the question is that how to divide a document into homogeneous segments. And when I discussed how to divide our external collection to the segments, I said that you may believe that each segment contains both query and answer. This is an informal criteria to divide the collection into segments. But maybe the question also how to model very short text such as Twitter messages.
Just 4 or 5 words per document.
Yes, this is another problem. If your documents are very, very short, there are some techniques how to make the model better. The first technique is to use big grams, 3 grams, etc. Another technique is to use B terms. Bitems are pairs of words that co-occur in the document, in the short message, but not nearer to each other. Any pairs of words of short message. And this is an artificial way to make the document longer.
In skill model case, as I understood, we have metrics like document starts and track prices, right? In multi-model case, we have metrics like documents, terms, model 1, terms, model 2, or we have a data.
We have a matrix. Phi become a matrix divided into blocks. Each block describes one modality. So this is modality of words, this is modality of bigrams, this is modality of users, etc. But for each modality, the requirement is that columns must be normalized. So the normalization constraint is for each block, not for each column of the overall matrix, but for each block. This is the only difference between one modality and several modalities.
Yes, I have some simple question, and you could understand some intuitive reasons behind you say that we have the LDA technique, we have the formula, and then we can generalize this formula. Right? Yes. And then I'm thinking while listening, let's say we solve some example text problem. So we can solve it, we can compose system in a different way. We can, let's say, compose separately, component by component, so syntactic process, semantic, named entity, and so on. Just separate. Or on the other hand, we can compose the whole system, neural network system. Right? And then I see this technique LDA. So, and then my question is, why not we just use LDA and plug it in into, for example, neural network system? Why do we need to generalize this formula? What is it? How does it help us? Is it to save states, or is it faster execution?
Thank you very much for very, very simple question. It's so simple that I delegate this question to my PhD student.
Ну, мы не в Америке. So, if I understand you correctly, if you have this general system, still you need some unit that stands for topic model, and you might need some more requirements on this single unit. So it's if you said that you have syntax and then semantics and something, but still, if you want a topic model to be, for example, interpretable, or you have some other requirements on your topic that have been discussed, then you need to generalize exactly this part of your general system. Or probably I also misunderstood you. Yes. So, if I understand correctly, the not the advantage, but it depends on your task. So, if you want your topics to have some requirements, then it's there is no need to make some other parts of your system better, right?
Okay,
Okay, probably.
with the presentation.
Okay. So probably I'm not convincing, and we can discuss it afterwards. So yes, thank you. I hope you still have some energy to listen, and I will try not to take you for too long, and you can interrupt me with questions whenever you want. So let us get started. During the last dozens of years, there has been a lot of research that fall into two big groups. The first path starts with bag-of-words representations, then quite popular method of latent semantic analysis, then performs truncated SVD. And then some people generalize this method to come up with probabilistic latent semantic analysis, LDE, and many other probabilistic topic models that are shown to be quite useful if you want to organize your data and to visualize and interpret. But this is one side, and the other side is a newer, a more recent branch that also starts with bag-of-words representations and then goes through neural language models. These models are usually quite complicated and time-consuming, but recently they have been some sort of simplified and resulted in models that learn word embeddings. So the most recent papers of Nikolaev and Stanford group and Levent Goldberg, and it's surprisingly that these models are rather similar to what people did before, but these models perform really well. So some general concept that underlies both branches might be vector space models of semantics. So what is it about? It's quite general phrase that describes a big group of methods, but it's common for all of them that we have raw corpus and we preprocess it somehow to get some metrics of corpus-based statistics, and then we perform dimensionality reduction and result with some useful vectors that can help us to measure similarities between the concepts. And this approach is quite related to distributional hypothesis that tells us that words are similar if they occur in similar contexts. So with this in mind, let us have a closer look at both topic models and word embeddings. So in both cases, we learn some latent vector representations based on prediction of corpus-based frequencies. In case of topic models, we learn probabilities of words and topics and documents. So we have vectors for words and vectors for documents that have this probability constraint of non-negativity and normalization. In word embeddings, we do not have these constraints. We have real value vectors for words and for contexts. And in most cases, these contexts are also just words from the same vocabulary. So from this point further, I will assume that this C word is also an ordinary word from the same vocabulary as my W word is. And based on some common applications of both techniques, we can say that here the main idea is to have interpretable components of the representations, and here to have meaningful distances between the representations. As for the second part, there is some freedom to decide what frequencies to model, so what conditional probabilities to model. Topic models work with global probabilities of words and documents, and these word embedding models work with local context. So in continuous bag of words model, we predict the next word based on its nearest neighbors. And in skipgram model, we make vice versa. And in paragraph to vec model, we combine both these ideas. So we use vector for document and vector for nearest neighbors to predict the current word. Thank you. So once we have decided what probabilities to model, we still have freedom to decide how we are going to model them, right? So in case of PLSA, we have these probabilities as parameters of our model. So it's quite simple. We can just make a mixture distribution of our topics to get the probability of words in documents. In case of skipgram, we have real value score, this dot product. So we need to use softmax function to transform it to the probability of word. And this is some important distinction between two of them. So in both cases, we model some probabilities, but we make it in different spaces. And let us go further. And once we could model the probability of single words, let us model the probability of the whole corpus. So let us compute the log likelihood for both models. For PLSA, we can observe a number of documents and words in them. We observe each word NVD times. And so here the log likelihood comes. And in skipgram model, as we decided, we wanted to predict a local context based on each word in a corpus. And we can say that, assume that there is conditional independence. So we just model it as a sum of individual probabilities for words based on given another word. And now let us aggregate the counters, right? So let us think how many times each couple of words, V and C, occur here in this formula. It's simple. It's just how many times the word occurs near another word in a local context in the corpus. So can we define a document in such a way that this counter has exactly the same meaning as this counter? Yes, so if we speak about some concrete word, any word, and we take all its local contexts and collect them together, local context of all occurrence of this word, we will get some pseudo document that is associated with this red word. And the number of times where other words occur in this document has exactly the same meaning as this counter here. So the point is that if we train a topic model based on this collection of pseudo documents, we have them the same number or as the size of our vocabulary, then we can model the same probabilities, the probabilities of words given another word in its local context. So let's move on and come to optimization problems and optimization techniques that are used to solve all these tasks. In case of PLSA, it's quite straightforward. So we have log likelihood, and we would like to maximize it, and we use EM algorithm that has been covered today in at least 2 lectures. And the maximum is achieved when the dot product is equal to corpus-based probability of words in a document. So we can treat this as a problem of matrix factorization, where we have probabilities of words in documents calculated just by corpus, and we perform a low-rank matrix factorization into matrices of our parameters. And absolutely the same thing is true for word embedding models. So here for GLOVE model, Global Vectors model proposed by Stanford group, they have another loss function, and they have even another space because, again, these parameters are real values. But again, we have some optimization problem that we would like to minimize with respect to our perimeters. And the optimum of this squared loss function is obviously in a logarithm of word co-occurrence frequencies. So we can treat this problem as a matrix factorization of these values, log co-occurrence frequencies, into two matrices of perimeters, psi and psi dash. And in case of skipgram, there is not so easy to optimize the direct formula for skipgram that we write it down here. And Dmitry Vetrov has presented one approach, which is hierarchical softmax, to approximate it. And another approach, also proposed by Mikolov, is to use negative sampling when we say that we would like to have bit probability for those couples of words that really occur in the corpus. And also for each word, we would like to have some negative contexts. We would like to sample them from some uniform distribution, and we would like to have small probability to find this couple of words in the corpus. So this is why minus is found here. And this optimization task it's not so obvious which is the optimum or what is the optimum of this task, but Levy showed that quite known statistics, which is called shifted PMI, pointwise mutual information, gives the maximum for this optimization task. So this is the, again, matrix factorization task for these corpus-based statistics. Here are just co-occurrences of two words and the number of each individual occurrences of words. And again, we perform a matrix factorization with another loss function. And both these methods used stochastic gradient descent-based techniques. But it's important to mention that in this one, in stochastic, skipgram negative sampling, we do not aggregate the counters altogether. So we never see the metrics that we factorize. We just use the couples from the corpus one by one and update our parameters. So to take it in a nutshell, we have a matrix of some co-occurrences that and it is our decision how to cook it. And even if we use some word-to-vec method, implicitly we decide which elements will be found in this matrix. Then it is our freedom to decide which matrix factorization technique to use, whether it will be stochastic matrix factorization with non-negativity and normalization constraints, or will it be some other techniques with no restrictions and so on. And then the resulting representations can have different qualities that may be used in NLP tasks. And once again, there are quite a lot of small solutions here, for example, for cooking this matrix. The same solutions as have been always studied in vector space models, and they really make the result different. So I mean that the performance of different models really depends on these solutions. And if we take just only two solutions, whether to model probabilities or not, and whether to use word document metrics or word metrics, we will place topic models and embedding models here. And this paper is quite successful in modeling word document co-occurrences using softmax function, as word2vec does. And what about this cell? Well, firstly, it is shown to perform well for short text. So it's one more answer to the question that was here. Because if the texts are too short and sparse, then it can be useful to count word-to-word co-occurrences. And two second points are covered in two final slides. So these topic models for word-to-word matrices can be useful for similarity and analogy tasks that are successfully solved with word embedding models. So this is just preliminary results of PLSA topic model on these pseudo documents or word-to-word metrics. And for example, for these words, we can see that we can go from masculine name that is quite popular in Russia to feminine names that are also popular in Russian by this operation. And here from the masculine name, which is popular in Europe, we get some other European feminine names just by these summoned add operations. And note that we have log here because we use just phi metrics, so the metrics of probabilities of words in topics for representing a word. And to get back into the space of real values, we perform logarithm. And finally, why this approach might be useful for this task has been partly answered already. So the documents have heterogeneous structure, and it's rather ambiguous how to split them into paragraphs. And to make local concurrence to influence the topics, we can use these word-to-word metrics to learn phi. So this is the first step when we use pseudo documents to learn phi and theta, and then we can disregard theta and use phi as a good representation of topics. And once we fix phi, we can use it to infer theta for any text paragraphs that we wish. So we can just aggregate it or perform several steps of EM algorithm using these fixed phi vectors. Thank you. That's all from my side.
Negative sample. It looks very similar to noise contrast estimation. What is the difference?
Yes.
Is there any difference?
Yes, it is really similar to noise contrastive estimation, and the comparison can be found in Mikolov paper. So they say that they just simplify a bit this known technique because they do not need all that it provides and make it a bit faster and more convenient for them. So as far as I remember, it's important that they just sample these negative examples, and it results in a faster technique for them. And they also have some comparison of performance results in terms of quality, both for them. They sample from uniform distribution over words, and they show that it's better to power it to 3/4, just because empirically it behaves better.
Okay. In one of the slides, you say that it's maybe a good idea to use topic model on word metrics.
Mm-hmm.
Yes. If I remember correctly, in Levy works where he prove equivalence of factorization and classification information, they try to factorize word coherent matrix by
Right.
Why modeling should be better than just SVD?
Well, it must not be better. So at least it is one more variant, one more option to factorize this matrix, and it is rather different. So for example, somewhere here We have latent semantic analysis that also makes SVD, and we have other models, topic models that that work in probability space. So it is just one more variant that can perform either worse or better. And this Levy paper also says that one more good idea is to try stochastic matrix factorization, but they just leave it for further work.
The goal of our research is to join advantages of both approaches. In topics models, we have interpretable coordinates of vectors, and in Vortovec and company, we may solve the problems of associations and similarity. And so the joint model may be possible that will solve all of these problems at once.
I'm sorry, it's not exactly on this topic. You are given this pairs of words. But there is a known idea of Alexei Ivakhnenko, which was called GMDH or GUA, which because why pairs? Maybe some pairs have less probability than triples and so on. So haven't you tried the approach which uses in homogeneous length of this combination of words for the same purpose?
Maybe I didn't understand your question. As to me, the method GMDH is about model selection and about feature selection, not about dimensionality reduction. And matrix factorization are about the seeking short representation of data. This is another task.
More questions?
Okay, let's finish one.